Hello friends, welcome to my channel. Today in this video we will learn about the fluid bed process and we will also learn how to scale up the fluid bed process. So let's start the video. So friends, there are different type of the fluid bed process. For example, top spray granulation process in which we granulate, in which we do granulation of drug substance and excipients. The binder solution we spray from the top, and the uh, particles, the drug substance excipient mixture will fluidize in the air by the inlet air by the which comes from the bottom. So this is the top spray granulation. Then bottom spray coating, this is used for coating the particulates, small particles, and also for tablets also. So there is a one Wurster column where there will be a spray zone and where coating will occur, and this movement of the particles in the Wurster column will be upbed, and then there is an expansion chamber where particles will come to the down, and again it will come in this partition column for coating by the venturi action. The gun will be mounted in the bottom. So in the top spray, the gun will be mounted on the top, and the bottom spray gun will be mounted on the bottom. So these are the two fluid, generally known, generally used as a fluid bed processes. Also, tangential process is also used in that the gun will be mounted at the tangential position. Particles will rotate like that, and they will coat it in the tangential manner. Some new fluid bed system also came in which there are orbiter based systems where gun will be in the at the center of the center only, but the gun will rotate, and during rotation it will coat the particles. So these are the different types of the fluid bed processes. So friend, in this video we will focus mainly on the process part. So we'll mainly focus on the process part, but uh, one question comes when we want to design our manufacturing process as a Wurster process. Then Wurster process means bottom spray coating. When we want to design our process as a bottom spray coating, then one question comes in the mind of the formulation scientist, that how to select the starter palette. So just I will give a brief idea of that. That it is the rule which is trusted by most of the pharma professionals, that for selecting the starter palette, what to do, we need to count the number of pallets in the reference product. See, for making a robust formula for the bottom spray, it is very important to select the right starter palette. So the starter palette, whether it will be a sugar sphere or whether it will be MCC sphere, that we can select based on our desired final outcome, and as well as based on the what is required by the what is used by the reference product. Okay, so based on that we can select our the starter palette. But how to decide the size of that starter palette, that which size we have to select, so that we can decide by counting the reference product starter palettes. So we will count the reference product starter palette, then we will evaluate different available starter palette in our which we want to start with. So different available starter palette we will evaluate, we will match the count. Based on that we can select the right starter palette, so that after coating, after desired coating, our final count will match with the reference product count. For example, if I am developing a generic version of a reference product, and then I will count, if it is in a capsule form, I will just open the capsule and I will count the number of pellets. Or if it is in tablet form, then I will disintegrate the tablets, and by separating the water insoluble and soluble portion, I will able to count the number of pellets. Then if reference product have used sugar sphere, then I will take different ranges of the sugar sphere, like 40, 60, 60, 80, like that. Different sizes of sugar sphere I will take, and then I will count the number of the sugar sphere. Whatever size matches that size, I will take to as a my starter palette. And after final coating, I will again count, or I can check the size of the my pellets with the reference product palette. In the count and the size, both should match. Or we can go for the same study also. Based on that, we can conclude that we have selected the correct starter palette. So starter palette selection is the main one of the main activity in the development of the Wurster process. So friend, this is the Wurster column. You can see this is the partition column, and here is at the center there is a gun in the bottom. There is at the center of the partition column there is a gun, and this is the top view of the Wurster column. So basically there is a partition column, there is a gun, and there is a mesh size to prevent the loss, and there is a air distribution plates. So this is, you can see the air distribution plate. So air distribution plate have different holes. There are bigger and more holes in the center of the plate, which uh, allows air to flow in such a manner that it will make a upbed, and particles will move from this partition column, and from the bottom spray comes, and this will be the spray zone, and coating will happen in this spray zone only. And after coating, particles will go in the air and in the expansion chamber, and they will fall down, and again by venture reaction they will go like this and this, and again by coming in the spray zone, coating will happen. So this is the top view of the bottom spray Wurster column. Let's understand same thing by this diagram also. So this is just a pictorial diagram of the Wurster column. This is the partition column, and this is the spray zone. Here gun will be there, and inside the partition column there is a upbed region from where particles will move at the upside, and by coming in this spray zone they will get coated, and after going above the partition column they will fall in the expansion chamber, and again they will come here, and by the venture reaction again they will go there. So like that particle will come here, get coated, again go upside, and get dried, and again will come like that, buildup will occur. So the air for moving the particles will come from the inlet air, and inlet temperature we can set to dry the particles after coating. So this is the pictorial diagram of the Wurster column. So one of the main thing is air distribution plates. So air distribution plates helps us to get the desired airflow. So based on the particle size, we select the air distribution plate, which we'll discuss in this video in the next slides. So friends, as I discussed earlier also, that in this video we will focus on the process part of the Wurster process or top spray process, that how to scale up these fluid bed process, that we will discuss in this video. So process variables of the Wurster based pellet coating are as follows. Like first, equipment variables. So in the equipment variable, equipment itself is a variable. So equipment make, that across the scale, whatever equipment you are using in the lab, and whatever proposed equipment for scale up and EB batches, the geometry of those equipment should be same. So equipment is one of the variable. So based on that we will design our scale up strategy based on the equipment in which we developed the product, and the equipment in which we are about to take scale up batches or EB batches. Based on that we'll design our scale up strategy. Then Wurster column diameter. So Wurster column is partition column. So partition column, the spray zone will be inside the partition column only. So based on the Wurster column diameter, our scalar factor will be calculated, we will see in the next slides also. Then air distribution plates. So the air which will move the particles to the upside, and the air which will allows particle to fall down, so that it will again come into the spray zone, that is controlled by the air distribution plate only. So selection of the air distribution plate will depend upon the size of the starter pellet, as well as the particle size growth during the coating process. So how to select the starter pellet, this will see in the next very slide. Then column height. Column height means there is a gap between the partition column and the base of the Wurster. Base of the Wurster means air distribution plate. Above the air distribution plate there will be one sieve to prevent the particles to go inside. So the partition column will be at some height from that air distribution plate and sieve, so that venturi action will form, and the particle can go inside the column for coating purpose. So this column height will depend upon the base size, so that a uniform movement should be there. And to decide the column height, one thumb rule is that maximum number of particle should pass through the column. Means column should not be remain empty. So this comes by the experience only. So by observing your process, you can learn that column should not be empty, because if less number of particles will pass through the column, then chances of tuning formation or sticking will increase. So maximum number of particles should pass through the column, and the movement in the downbed side should be uniform. Means it should not be very aggressive, and it should not be there should not be no movement. So that is smooth, that light bumpy movement should be there. So based on that, we'll decide our column height. Then nozzle tip air cap position and nozzle tip diameter. So this is the nozzle size, which is very important, and nozzle tip air cap position, because based on that air cap na, the distribution of the spray will depend. So generally thumb rule is that you keep around 1 mm 2 mm air cap down from the nozzle. So based on, if you do that, then you can observe the proper V-shaped spray, and it will ensure there should be no tuning or no sticking of the spray in the column itself. The number of nozzle is also equipment variable. Filter bag, type of filter bag you selected, that is also a equipment variable. So these are the equipment variable. Then in terms of the formulation, the solution and dispersion preparation variable are solid content, so solution dispersion viscosity, delivery pump, and hold time of the dispersion. Then preheating variables are inlet air dew point, shaking interval, duration, inlet air temperature, product temperature, air volume, atomization air pressure, preheat time. These are the preheating variable. Then spring variable, inlet air dew point, shaking interval, duration, inlet air temperature, product temperature, air volume, spray rate nozzle, spray rate per nozzle, atomization air pressure. Then drying variables are inlet air dew point, inlet air temperature, inlet air volume, exhaust temperature, atomization air temperature, and drying time. These are the process variables of the Wurster pellet coating. So friends, generally for the generic development, first we develop in the lab. So in the lab, we based on the our process, what product temperature is required, we set our inlet air temperature. So based on the our process, what product temperature required, we set on our the inlet air temperature. So for scaling of the product temperature will be scale independent factor, so it will be same across the scale. To achieve that product temperature, we will require the inlet air temperature. So based on that, we can adjust. So there is no scalar factor for the inlet air temperature or product air temperature. Okay. Second, shaking interval and duration. The purpose of the shaking interval is to clean our bags, so it will be also remain constant. So whatever we are using in the lab scale, similar we should use in the plant scale or based on the vendor recommendation. Second thing is air volume and the spray rate. Air volume and the spray rate, these are the scale dependent parameter. This we will learn in this video, how to scale up the air volume and the spray rate. Also atomization air pressure. The purpose of the atomization air pressure is to atomize the our solution. So this also is scale dependent parameter, and we will learn in this video how to scale atomization air pressure also. So one most important thing is inlet air dew point. So that is also important factor. It is also scale independent, but how to set that inlet air dew point, or how to what is the role of the inlet air dew point, that also will learn in this video. So as I told, that air distribution plate is an important equipment variable. Purpose of the air distribution plate is to distribute the air so that a right combination of upbed and downbed can be maintained. Based on that, particle can coat uniformly. So this is the general vendor recommendation, and based on your vendor recommendation, you can proceed. So based on the size of the particle, we select the air distribution plates. In the lab development models, generally a single plate used, but in the commercial models or scale up models, combination of two plate used. So why in the lab scale development model we'll use single plates? Because in this plate only that type of hole which can give proper up bed and down bed, that are available. But in the commercial scale, as our base diameter will increase, so two plates required. By the combination of these two plates, by the combination of two different sizes hole, we get a proper up bed and down bed movement. So you can take screenshot of this, and based on the same you can follow to select your air distribution plates or as recommended by your vendor. So friend, dew point is a very important factor in the important thing for the fluid bed coating. So generally what we assume that the inlet air which comes from the bottom, or which comes from the bottom, so it is hot air. We maintain its temperature by the inlet air, by inlet temperature. So in the spray zone, we spray solution to the particles, then particle will be dried while coming to the expansion chamber by the inlet air, by the temperature of the inlet air. But apart from the temperature of the inlet air, the drying efficiency of the air will depend upon the moisture humidity present in the air also. So that humidity also affect the drying efficiency of the machine, the drying efficiency of the process. And based on the drying efficiency, the coating thickness of the polymer, if you are doing MR or DR coating, as well as normal drying also will affect based on that humidity. So for that dew point control, or to maintain a constant absolute humidity from development to the scale up models is required, so that the seasonal variation or any variation in the due to the equipment or season can be avoided by keeping the constant absolute humidity, or maintaining the same dew point. So let me read this so that we can understand that in addition to the temperature, humidity of inlet drying air also affects the drying of coated particles. The relationship between temperature and relative humidity or moisture content of air at different atmospheric pressure may be derived from the psychrometric charts. So psychrometric chart you can able to find on the Google also. So how to read that psychrometric charts, you can easily read that. If you have any concern, you just mail me. I will make one video also how to interpret the psychrometric chart. So what this line means, that the relative moisture, what is the relative humidity at a particular temperature, the air present in the moisture present in the air divided by the maximum capacity of the that volume of the air to hold the maximum moisture. So that ratio is known as the relative humidity. So based on the temperature, the relative humidity or moisture content of the air will be different at different pressure. So that relation we can understand by the psychrometric chart. So main thing is that if temperature variation is there, something is there, then at different pressure air may have different moisture, different humidity, which can affect the drying of the coated particles. The humidity of air may vary from season to season or day to day. The changes in dew point of air changes the evaporating efficiency of that air. Lower humidity in the inlet air will enhance the drying capacity of the air even at low temperature, but it will cause it will if low humidity is present in the air, then it will enhance the drying capacity of the air. And if we use low humid air in the process, then it may cause excessive static charges also in the product. To eliminate static charges and process variability, the required specific and absolute level must be set in the initial stage of the development itself. What we want to say that here, that we should know at what humidity we are working in the development stage itself. To get a reproducible process, we should know at what humidity we have set the process, and the same humidity levels should be maintained in the scale up model also, because the drying efficiency of the air depend upon the humidity. So that humidity should be kept constant. Either your machine can be controlled by the dew point also, or can be controlled by the absolute humidity also, but you keep the same absolute humidity in the development as well as in the plant scale also. This is the learning from this slide. Now friends, for best size calculation, some formulas are there. Just I am telling just for information only. Generally working volume can be provided by vendor only, and the same working volume we can follow. For example, if top spray granulation, if we have working volume by putting the gun at the lower position. we have working volume by putting the gun at the upper position, and based on the available working volume we can calculate our base size by a simple formula: rho equal to mass upon volume, mass equal to rho into volume. So density of the our product multiplied by the working volume, we can calculate minimum and maximum of the base size, minimum and maximum base size of our product. So but if some cases if it is not available by the vendor, then we have these some formulas. The formula are same only, that minimum and maximum base size can be calculated by the equipment volume multiplied by 80% multiplied by the BD. And for minimum they have taken zero point 0.5, means 50% of the occupancy, considering only one nozzle. So this is a old formula. But if we don't have working volume, we can use that 50 to 80% or 30 to 70% based on the equipment capacity. We can utilize for the top spray granulation, and based on that we can calculate our base size. So this is just one formula. For tangential spray granulation also, minimum and maximum base size can be calculated by considering 20 to 80% as recommended. Now for bottom spray granulation, see bottom spray coating. See what bottom spray coating, as we see, there is a partition coefficient. Because of that partition coefficient, the space will be reduced. So to calculate the base size, this formula is there. So in that, what we are doing, pi r1 square h, which is just we are considering it as a cylinder. Cylinder volume is pi r square h. So this is the pi r square h. R1 is the radius of the chamber. So complete chamber volume minus radius of the partition coefficient. So this is the volume of the partition. So complete chamber volume minus partition volume. So we'll get the in between volume. So that volume multiplied by the BD will give the our base size. Rho equal to mass upon volume, mass equal to rho into volume. So rho is the BD, and volume is the for the top spray and bottom spray, it is a volume of for top spray and the tangential spray, it is a volume of the container. But for bottom spray, it is the volume of the container minus the partition volume of the partition volume, means the volume of the Wurster column. So n is there. If we are using more Wurster column, then number of the Wurster volume column can be multiplied here. So based on that, we can calculate our maximum base size. And considering 50% base size, they calculated the minimum base size. This is a formula if you don't have the vendor recommended base size. But generally, if you have a good vendor, they will provide their working volume. Based on that working volume, you can calculate the your base sizes for you can calculate your base sizes right now. So based on the recommended by the vendor. But thumb rule is that from lab scale to the plant scale, you keep your base size constant. You keep your passage constant, means not passage constant, you keep your occupancy constant. What I mean, that you keep your occupancy constant. So and based on the volume of the equipment, that passage factor will come. We'll discuss, we will learn same thing by a simple example in the next slide. Now friends, we will learn to calculate the scalar factor by this simple Excel sheet, which I just pasted in this presentation. So as I told earlier, that inlet temperature, it will depend upon the desired product temperature. So based on the whatever product temperature you desired, for keeping the for maintaining the same product temperature in the scale up, you will keep the inlet temperature. So this is scale independent right now. Height, Wurster column height, there is no set rule. But what I can tell you, that the you means it is observation based. So the we will select that height, that column height, so that maximum number of particles should pass through the column. The column should come full. And also that in the down bed, the movement of the particle should be smooth only, means all particle, you can visualize that all particle are going from the pellets, from going from the partition column, the Wurster column, and coming down, and in the at the downside also there will be one the smooth movement, not very aggressive movement, and not there, and there shouldn't be not be no movement. So the smooth bubbly movement should be there. So based on that you can adjust your Wurster column height, and you can keep it constant. And if required during the process, if your base size of buildup is increasing, then you can slightly increase your Wurster column height, so that to maintain the uniform motion of the pellets from the column as well as at the downbed area. So based on that, then this main scale up main parameters in which scale up will apply, that are inlet air volume, that is inlet air flow, and spray rate, then automation air pressure. These are the three main variables in which scale up factor will apply. Second thing is this batch size. So as I already told you, that working volume will be provided by vendor. A good vendor will provide you the working volume. So to calculate the best size, you can calculate the factor from the working volume. For example, this is a lab model of one of the vendor. So the working volume is 2.4 liter for the bottom spray, and here this is the scale up model of that vendor, and the working volume is the 84 liter. So 84 divided by 2.4 will give a factor of the 35. So same 35 factor you can use for the scaling up of the batch. For example, in the lab scale, if somebody is taking 600 gram batch size, then it will come to the 21 kg batch size for the 21 kg batch size for the scale up model. So based on the working volume, minimum and maximum working volume provided by the vendor, we can decide our batch size in the lab model. And by using this factor, we can increase, we can scale up our batch size for the scale up model. So if vendor is not supporting, then working volume you can calculate by the formula told by me just in the earlier slides. So based on that also we can calculate the factor, and we can calculate our batch size by the using those formulas. Okay, then the how to scale up spray rate, air volume, and the automation air pressure. So for that we will calculate one factor. That factor we can calculate by dividing the Wurster column base area, cross-sectional area of the Wurster column of the scale-up model by the lab model. So it will give a factor of the 9, 0.0377 divided by 0.00041 will give a factor of the 9. This 9 factor we can use for the scale up of the airflow, spray rate, and automation air pressure. Also, you can calculate this area by you can measure the Wurster column diameter. So to calculate the area, it is simple. Pi r square is the area. So Wurster diameter divided by 2 will give the Wurster column radius. Then you can use pi r square formula, and you will get the Wurster column base area. In scale up also you have to do the same only. By that, by dividing scale up model by the lab model, you will get the factor. So by that factor you can decide what airflow you have to maintain in the plant. For example, in the lab model somebody is working for at the 9 CFM. Okay, so in the scale up model the CFM will be 81 to start with. Then based on the observation they can vary as per the requirement. So to start with they can use a factor of the 9. Similarly for spray rate also, if somebody is working from the 10 to 20 gram per minute, so for the lab for the scale up they can have a range in the mind, 90 to 180 gram, provided that their guns also of the similar principle. So if the guns also of the similar principle, then they can take a direct 9 scale up factor in this case. So generally we cannot increase spray directly, right? So we increase it in a sequential manner. So similarly we can increase in a scale up also in the sequential manner, and the minimum and maximum ranges can be obtained by calculating the scale up factor, and the time in which we have to increase the spray rate then can be fixed in the development scale up itself based on the pellet increase of the pellet stage, and same can be followed for the scale up in the scale up scale also. Then automation air. So automation air pressure scale up, there are different strategy. Actually, we can calculate the in the gun at a particular automation pressure at a particular bar. There is a, we can calculate the amount of CFM, amount of the air passing. So generally vendor have that table. So by we have to scale up that air only. For example, if we are keeping one automation bar in the development, and then the CFM is 1.2 CFM, then we can multiply by 9, and in the plant scale we require 10.8 CFM. So corresponding that we can calculate, we can keep 2.5 bar as a automation. So at what automation what CFM is available, that chart you can ask vendor, he will provide that chart, and based on that chart you can propose your scale up atomization. This is the one way of scaling up automation air pressure. Some other ways are also there. You can measure the droplet size by using some instrument like spray tech is there, which use the principle of the laser diffraction. So based on the laser diffraction principle you can measure the droplet size at the lab scale, and then you can study your gun at the scale up scale also, and you can match the droplet size at the both scale, and you can keep automation air pressure to scale up the process. So that is a good way of doing that thing. If you don't have that instrument, then you can use a simple CFM factor, and based on the observation you can decide your atomization. So these are the way to calculate the scale up factor for these three important parameters. And this is the similar way for top spray granulation also. We can calculate our airflow as well as our spray rate based on the similar principle only. So friend, this is all about the scale up of the critical factors in the fluid bed process. But what we discussed that one of the important factor is dew point also, the absolute humidity of the inlet air. So we should always keep the same inlet air absolute humidity, and we should know that in the lab scale at what humidity we are working, and the same humidity we can keep for the plant scale also. So if you have any doubt, you can write to me, and you can tell me so that I can make a more elaborative video also on the same topic. Friends, thank you very much. Thank you for your time. If you like the content and efforts, please share the video to your official social media so as to motivate us to bring more such video. And thank you very much. Thank you again. Write to me if you have any concern so that I will also get the feedback, and I will come up with the new videos on the topic desired by you. Thanks a lot.